Okay, Assalamu alaikum. Let's continue. We were studying one-dimensional heat transfer, conduction, steady state, and in this chapter we already covered the fins. Okay, and now we move towards the array of fins. Okay, normally fins are used to increase the heat transfer. Okay, but we do not just put a single fin, we put many fins on a pipe or on a plate or whatever. So we don't put a single fin, we put many fins, and they are very arranged in an array. So we call it an array of fins, fin array. Fin array means something arranged in sequence. Okay. So if we have an array of fins, then how do we solve the problem? Okay, so suppose we could have a flat plate. Over that we can have straight fins. We can have a tube over which we can have annular fins. Okay. Now we define certain terminologies. Okay, first of all, a terminology is the AT, total surface area. Total surface area means total surface area. So that means that's the total surface area. For example, in this case, it was a surface area here, then here, then here, then at the bottom, then here, here, at the bottom of this fin, there. All complete surface area is the total surface area. Okay, with the fins, everything. Okay. Then we have another terminology is AF, which is the surface area of a single fin. Okay, so if we take any one of the fin, so for this one fin only, what is the surface area of that one fin? So for example, in this case, in case of the straight fin, it will be the top area here, the bottom, and the sides. That will be the surface area of heat transfer for that single fin. Okay, then we have the prime surface area. Okay, it's written as AB. AB, B referred to the base. Okay, so you see here you have a surface and or the plane over which there are many fins attached, but there is certain area where there is no fin. For example, here, no fin here, no fin here. So collection of all those areas where you do not have fin, that is known as the prime surface area or the base area, like that. Okay, so we have so if I define, so I have total area is equals to area with fins and area without fin. Okay, total surface area is area with fins and area without fin. Okay, so area with fins plus area without fins, that will be the total surface area, right? So if we talk about what is the total surface area without fins, so without fin is the AB, prime base area, surface area, right? And with fins, so I have the surface area of one fin multiplied by the number of fins. Okay, so surface area of one fin is AF multiplied by number of fins is N. Okay, so we got this main formula. Total surface area is equals to number of fins multiplied by the surface area of one fin plus the base area. Okay. Okay, now let's talk about overall efficiency. Okay, so basically heat transfer, overall heat transfer will be what? Look, overall heat transfer will be heat transfer from the fins plus heat transfer from the base. So we have the total surface area is composed of the area with fins and area without fin. Okay, so total heat transfer will be the heat transfer because of this area plus because of this area, right? So total heat transfer, so QT, if I say that, that's the total heat transfer. So QT will be HA delta T plus HA delta T, right? It's like that. HA delta T plus HA delta T. Now, for the case of the base area, So the base temperature is Tb, right? So delta T would be T base minus T infinity, right? For the case of the base area, okay? So delta T base minus T infinity, or here it will be AB, okay? And T base minus T infinity is what? Theta B. So I can write here theta B, right? So we have this theta B, okay? Now let's come over to this one. We have H, okay? Delta T here will be, okay, you remember, in case of the fin, we know that the fin temperature is not the same as the base temperature. But if you remember, we define fin efficiency, and we say that if we assume that the fin is at base temperature, then if we know the efficiency, then multiply by that Q max, this will give you the fin heat transfer. Okay? So this total heat transfer is what? Heat transfer from the base plus heat transfer from the fin, right? So this QF, the heat transfer from the fin, we can represent as, here we can put delta T as theta B with the efficiency of the fin. Are you getting it or not? This is what we did last time. This is what we did when we were studying the efficiency of heat transfer, the efficiency of fins, okay? So we said this, efficiency of fin is Q of fin over Q max, assuming that the fin is at base temperature, okay? So if this is the case, then our delta T here, we can put here as with the efficiency here, okay? Efficiency of the fin, we can put delta T as Tb minus T infinity, okay? Or it's, I can write here theta B, okay? So I can write it here like this. Is it clear? Okay. So now because of the efficiency I used, so that's why this is the Q max multiplied by the efficiency. Okay, now is one thing is that, let's talk about this area. This area is the area with fins, and we already discussed that this will be N into AF. Okay, so let me replace it with N into AF. Is it clear? So I just replace the area here in this case because this is the heat transfer with the fins. So it's with the N number of fins multiplied by the surface area of a single fin. Is it clear? So now this becomes our formula for the total heat transfer in a system where you have an array of fins. So you see here, it's the same formula written here, capital N. There is the capital N, okay? Efficiency of a single fin multiplied by H AF theta B plus H AB theta B, right? That's the same formula written there. So we determine this formula. This is the main formula that we are going to use now, okay, in order to solve for the total heat transfer from the body with having an array of fins. Convection, yeah, of course. So you have you add the fin so that there will be more heat transfer area for the convection heat transfer to occur. Okay. Now the thing is that still this formula is a bit complicated, and we want to write it as here this eta f is the efficiency of a single fin. Now we want to write it as an efficiency of the overall, as with an overall efficiency. Okay, so Q can be total heat transfer can be written as HA delta T. Overall heat transfer can be written as HA delta T, but in this case I want my delta T to be the maximum delta T, and the maximum delta T is if it is Tb minus T infinity. Right? Okay. So I want to use it as theta B while using the total area AT here, by using the total surface area. So now I have to multiply with the overall efficiency. Okay, so the definition for overall efficiency can be derived from this. Okay, so in this equation, if we take the three terms out, H, AT, theta B, then the remaining will be considered as overall efficiency. Now this derivation from here to here is not a simple one. You need to do a little manipulation here, because here you have AT, here you have AF, here you have AB, and AT is a function of AF and AB. So you have to do some manipulation. But anyways, you can do this. That's not an issue. And you have the final answer there. Okay? Now the final answer will be that this overall efficiency will be 1 minus NAF upon AT 1 minus eta F. This is the overall efficiency. Remember, eta naught is the overall efficiency for an array of fins. Eta F is an efficiency for a single fin. Is it clear? So my heat transfer from this heat exchanger or whatever the device is there with an array of fins is equals to eta naught HA delta T, where delta T I'm using the max, area I'm using the total, and that makes sense. So now I have to multiply it with an overall efficiency, and the formula for overall efficiency is this: 1 minus N is the number of fins into area of a single fin divided by total area into 1 minus efficiency of a single fin. Is it clear? So in case if you have a device with no fins, then eta naught will be? Eta naught will be? 1. Okay. Because then the whole body itself is actually at theta B, and your total area have no fins. So there is no fin, N0. So it's just the base area, prime area. Is it clear? So if you do not have any fins, then the efficiency here will be 1. Overall efficiency will be 1. Okay. If you have fins, then this will be less than 1. However, you will have a very large area here. AT will be very large, okay, because of the fins. Surface area would significantly increase. Is it clear or not? Okay. So how do we get this eta naught equals to this thing? Is by manipulating this. The only thing is that we have to just keep H, AT, theta B out and the remaining terms on one side, so then the remaining term will become this thing. Okay. Is there anything that you do not understand?
Is an exam need to prove that, or just like short question like this one?
I can ask you to prove that. Oh, okay, this thing can also be given as a proof. Okay. Okay, now there is one more thing added into it in here. Look, you have the main body and then you attach an extended surface to it. Sometimes it is attached in the designing phase. So when you are designing that device, you already know that you want to add the fin. So in that case, in the casting process, you made a provision for the fins, and the fins are integrally joined in it. So they are not separately joined. They are a part of the main body. Okay? So there is no joint here. So there is no joint here. It's a part of the main body. Okay? So because you know, whenever it is not part of the main body and it is joined separately, so there will be a contact resistance here. Okay? So the only difference is that if you have a contact resistance there, so the formula for overall fin efficiency would modify a little. Okay? So this is the formula for overall efficiency, that's written there, but in case you do not have any contact resistance. In case if the main body was made earlier and the fins were attached later, like pressed, hammered into the main body. So then you will have a contact resistance here. And if you have contact resistance, then the overall efficiency will be modified from this to this. So it's almost the same formula there, except that it was initially 1 minus eta f. Now it is 1 minus eta f upon C1, where C1 is 1 plus eta f h, area of a single fin, into contact resistance divided by ACB. ACB is what? Cross-section area of the base. That's this area. The cross-section area of the base, okay, where the fin is attached. Okay.
So this should be much less efficient.
Yes, obviously, because you are adding a resistance here. You want to increase heat transfer, but the resistances are the thing which resist heat transfer. So you keep on adding resistances, the heat transfer would be reduced. Okay, so the overall efficiency will go down a little. Okay, but if you do not have any contact resistance, then this. If you have contact resistance, then this formula. Okay, and the contact resistance will be directly provided. How much it is? That's RTC that you're going to put here. Divide by ACB, area of cross-section area of the base, just the place where the fin has to be is going to be attached. Yeah, either it will be provided you from the table or it will be directly provided to you in the question. Is it clear? Right? Now the thing is that in terms of a thermal circuit, the base and the fins, because for the fins, with the fin efficiency, we are assuming that the fins are also at the base temperature. Because we are putting the fin efficiency, so assuming that the fins are also at the base temperature. So the temperature of the base plus temperature of the fins are all TB, right? Because with the efficiency we are considering. And so we have convection from the base and the fins to the outside, to the surrounding. So we have the convection heat transfer. Okay, so we'll have convection resistance. So we have convection resistance from the fin to the outside. We have convection resistance from the base to the outside. But at the base and the fin, the temperature is same. So if one point has the same potential, then the two resistances are in parallel. Two resistances are in parallel if at one end potential is same. Right? So here the potential is the temperature. So if the temperature is same on one end and on the other end, so it's TB to T infinity. So for the base it's also TB to T infinity, for the fins it's also TB to T infinity. Okay? So it's like we have the resistance of the fin and the resistance of the base both in parallel. Is it clear?
Like this, parallel.
Yeah, always like this. Okay. Now, however, in this case, when you have a contact resistance here as well, so in this case, the resistance of the fin and the contact are in series, but then this thing with the base are parallel. Okay? So resistance of the contact and fin are in series, but this thing, because the contact is at TB and this base is also at TB, so this thing to this thing is parallel. Is it clear? So consider this for the short questions, these diagrams. Okay? Okay, so let's have an example. Let's have a numerical problem. The engine cylinder is about the engine cylinder of a motorcycle. Previously, we don't used to see motorcycles here. Now we see a lot. Okay, I think now they are giving license. I think so. How so many motorcycles are now seeing on the street? Okay, the engine cylinder of a motorcycle is constructed from 2024 T6 aluminum alloy. Okay, so it's constructed from 2024 T6 aluminum alloy. This name is important because you need to take the properties from the table based on the name. Okay, and is of height 0.15 meter, and outside diameter is 50 millimeter. So basically, engine is like what? It's like a cylinder. It's normally we call it piston cylinder. So you have a cylinder inside piston. Yeah. So inside you have a piston moving up and down, right? So it's basically a cylinder. Okay. So this is the case. You have a cylinder, engine cylinder. Okay. And what is said is that the height is how much? Height is 0.15. And the diameter is 50 millimeter. 50 millimeter. Okay. Under typical operating conditions, the outer surface of the cylinder is at 500 Kelvin. So this surface, outer surface, TS, or I will call it TB here, base. TB is 500 Kelvin, right? And is exposed to ambient air at 300 Kelvin. So T infinity here is 300 Kelvin, right? With a convection coefficient of 50 watt per meter square Kelvin. So H is given. H is 50 watt per meter square Kelvin. Okay. Annular fins are integrally cast. How the fins are placed? Integrally cast. So there is no contact resistance. They are already a part of this thing. There is no contact resistance. Integrally casted. Okay. With the cylinder to increase heat transfer to the surroundings. Obviously, fins are there to increase heat transfer to the surroundings. Consider 5 such fins. So now how many fins they placed? 5. So 1, 2, 3, 4, 5. Okay. I have a very bad drawing, but I hope you are able to understand that. Consider 5 such fins which are of thickness. Okay, thickness of the fin is given. That's the thickness. Okay, that's the thickness. How much thick is the fin? Is 6 millimeter, and length 20 millimeter. So it's written whenever it says thickness, it means is this thing. How much thick is the fin? And the length. Length means how much from the base, how much it is extended outward. Okay, so that length is 20 millimeter. Okay, so look, the thing is that if the diameter is 50 millimeter, then the radius becomes 25 millimeter. So 25 millimeter is the outer radius, and then after that the length is extension. So it's 25 plus 20. So the radius of at the outside of the fin becomes 45. Is it clear? So you have 20 till the base, and then extension. Sorry, 25 till the base, then extension 20. So 25 plus 20 is 45 radius. Is it clear? And the thickness is 6 millimeter, and they are equally spaced. What is the increase in heat transfer due to the use of fins? So question is that what is the increase in heat transfer due to the use of fins? This means first you need to find out how much is the heat transfer with fins and how much is the heat transfer without fins. Then you subtract the two, then you know how much is the actual increase in heat transfer. Is it clear? So it is not asked what is the heat transfer. It is asked what is the increase in heat transfer due to the use of fins. So one time you have to solve the problem with fins, second time you need to solve the problem without fins, and then determine by subtracting the two, determine what is the increase in heat transfer. Do you understand the problem statement or not? Is there anything in the problem statement that you do not understand? Okay. Good. So let's talk about with fins. What will be the heat transfer? So we need to find this thing actually. We need to find QT, total heat transfer. That's with fins, right? And the formula is very simple. This is a formula.
We don't have the efficiency for the fin.
We'll find it. Okay. So formula is here. Okay. If you see in this formula, is h given?
Yes.
H is given, right?
Yes.
And what about this theta b?
TB minus T.
TB minus T, is it given?
Yeah.
Yes, TB is given. That's TB. T infinity is given. So theta b is also given. Okay. Now let's talk about this efficiency. Overall efficiency. So for overall efficiency, this is the formula. 1 minus n into area of a single fin divided by area of total area into 1 minus efficiency of the fin. Okay. So efficiency of a single fin, how do I determine that? What kind of fin I have? I have annular fin. So for annular fin, I do have the formulas as well as I have the graph. You remember? So if I go back for annular fin, okay, so that's the formula for annular fin. That's the formula of it. I need NF, right? So I can do this, but it's a very complicated formula. I can directly use graph, it's better. Okay, so if I go further back, so I had this graph. And that graph was supposed to tell me the efficiency of this single fin. Efficiency of the single annular fin, which I'm going to place here to get the overall fin efficiency. Is it clear? So let me just increase the magnification here. Okay. So that's the thing that we need to find out the efficiency. Okay. So in order to find the efficiency, first I need to know what is this term. Okay. So it's LC 3 by 2. So LC is the corrected length, and corrected length here is what? L plus T by 2. Do we know L?
Yes.
L was 20. That was the extension. So we know L, and it's also shown here. What does L mean? Okay. That's it. So L we know, and T is the thickness. Do we know the thickness? Thickness we also know. So we know what is LC. Okay. What about AP? AP is LC multiplied by thickness. Now we know LC multiplied by the thickness. You will know what is AP. So now you know AP, you know LC, you know H. What about K? Find from the table. For which material? Aluminium. Okay. Exactly. So you go into the table, find out the value of K. Now you know all of these terms. Okay. Once you put all the values, find out all of these terms, okay, then you go up, okay, and now you need to coincide with one of the curve. Now which curve will you use? So it says you use R2C by R1, okay. So R2C is, the formula is given. R2C is equals to R2, radius 2 is known, okay, radius 2 is known, it was 45 millimeter, plus thickness by 2. You remember why we are putting these C values, why we are using the corrected values? Because we don't want to use the tip heat transfer. These compensate for the tip heat transfer. Okay? So if I have an annular fin, so the tip of the annular fin will also be transferring heat, but I do not want to consider that. I want to add this into the length, into the length of the surface area. So that's why I'm increasing the radius, I'm increasing the length, okay, a little. That's the corrected length, corrected radius.
Which temperature, 300 or 500?
What temperature should we use? What do you think? Will you take the average? Average. It's clear? Now the thing is that, okay, so we have R2C. Now once you have R2C, okay, then R2C divided by R1, you will get a value based on the value. Now the curves are given for 1, 2, 3, 5. Suppose your value is 1.5. So then you make a curve yourself between 1 and 2. If it is 3.5, make a curve yourself from below 3, above 5, which you think should be closer to 3.5. Okay, intersect your line with that curve, go horizontal and find out the efficiency. Is it clear? This is what you have to do. Okay, when you are finding this way the efficiency, there is a possibility of slight error. Okay, so suppose if your if I'm supposing just if your value was for the x-axis was 1 and then you intersected here, so one thing is very clear, it is between 40 and 60. Right, okay, so if anybody write value above 60, it will be definitely wrong. Somebody write value below 40, it will be definitely wrong. But if somebody write value in between, I will consider it correct. 52, 53, 56, 50, 48, I'll consider that correct. Is it clear? As a margin of error.
This can be again the curve which curve I should use.
Based upon R2C upon R1. If R2C upon R1 is suppose 1.5, which one will you use? You cannot use 1, you cannot use 2, but it has to be between 1 and 2. So draw the curve yourself.
Oh, I know.
Yeah, I mean, imagine what would be the location of the curve and based on that find. Is it okay? So let's go back.
When we found the efficiency, what is the next step?
Okay, so now you find out what is the efficiency of the single fin. That's what you have found out. Okay, so this thing now is known. What are the total number of fins? Five. Five fins, right? So this thing is also known. Now we need to discuss about the areas. Okay, so let's first talk about area of a single fin. So what do you think is the area of heat transfer for a single fin? So if you see the fin from the top, it would look like this. Okay? Okay, so that's this area you need to consider. Okay? That this area you need to consider at the top as well as at the bottom. Okay? So now the one thing is that you know that this is R1, okay, and you know this is R2, but not just these, you also know that there is heat transfer from the tip, okay, but in order to compensate for the tip, you change the value R2 to R2C, okay. So instead of using R2, if you use R2C here, now you don't need to consider for the tip, just consider heat transfer from the top and the bottom. But the circumference, just you can ignore it because you change R2 to R2C. And that is when you are changing R2 to R2C, it is supposed to take care for the tip. It's supposed to take care for the heat transfer for the tip. Is it clear? Now tell me, who can tell me what is the surface area here in this region? What will be the formula for that?
Pi R2 minus R2C minus R1.
Yeah, but with the square. Pi r square, right? Pi r square is the area of the bigger circle minus pi r. So it will be what? Pi R2C square minus R1 square. Is it clear? So that will be the area, but that will be the one area. So you also have a bottom side. So multiply by 2. Is it clear? So that will be the area of a single fin. Okay. So now you have the area of a single fin. This is known, right? Now what will be the total area? This is very interesting. Total area is what? N into area of fin. So you know N. You know area of a fin. What about area of the base?
Base we have just R1.
Yes, exactly. So surface area of the cylinder. Is it clear? So what will be the surface area of the cylinder? Pi d.
Pi R1 square. Pi D square.
Pi dl. Pi dl. Surface area of the cylinder is pi dl. So that will be pi Since it's all written in terms of the radius, so I will say 2 pi r, which r? R1. R1, L is the height here, okay, h. But there is one thing you should remember, that is, yes, that is without fins. Now once you consider 2 pi r1h, so you have considered the complete with the fins as well. So you have to subtract the fin area, okay? You have to subtract the fin area. So it's not the complete length. The complete length minus how many fins you have? 5 fins, and for each fin thickness is t. Is it clear? So 2 pi r1, but if you put h, so that's complete area. But this is only without fins. So you have to subtract the fin ones. So that you have 5 thicknesses of the fin that you have to remove from here. Okay? So it's 2 pi r1 h minus nt. Is it clear? So now you have this thing. So now you know what is total area. Is it clear? Once you know total area, you substitute here, you will find out what is the fin efficiency. Is it clear? Once you know the fin efficiency, you already know the total area, you will find out what is the heat transfer with fins. Is it clear or not? So now you know the heat transfer with fins. Now, how can we find the heat transfer without fins? If we have heat transfer without fins, so that will be Qt is equals to, now this thing will be 1 without fins. So it's 1 multiplied by h. Okay, area will be what? Area total, but there is no fin, so this will be 0, it's just AB, and it will be 2 pi r1h, not minus nt, just 2 pi r1h. Okay, so that's the total area, but remember the total area will be 2 pi r1h here, that's it, not minus nt, because there is no fin.
But you multiply 2 by r. Why don't you multiply by r?
Because the formula for the circumference is pi dl. So put diameter into radius, it will be 2r. Okay, is it clear? You are seriously making mistakes in the areas. You have to focus what area you are using, because if you do these mistakes, so it will make horrible result in the exam. Try to focus what area we are considering. You need a lot of imagination in all engineering courses. That's the problem with engineering courses. You need to have an imagination of what's happening. Okay, so don't confuse in the areas. There are so many areas: circumferential area, cross-sectional area, blah blah. Okay, so don't confuse yourself into it.
When we take the heat from the without fins, when we eliminate NT, would it be double heat transfer?
Oh, so you are saying that this area will increase, right?
No, I mean when we eliminate NT,
Uh-huh.
we will take the heat transfer from all the cylinders plus
Yes, plus.
the fins.
No, but the fins is not there.
So
So n is 0. Capital N is 0. Because the fins is not there. So it's actually just the base area.
yeah, but wouldn't I sum it with the fins area in the end to find the total?
Even if you sum it, so you are adding this with 0. Anything plus 0 is the same thing. Is it clear? Even if you add it, then this is 0, so this term will go 0. Okay? So, eta naught, h, at, and delta t. What will be delta t here? Theta b. Theta b, that's it. Because the whole thing is at the base temperature. Now we are actually considering the base. Okay? So that's it. So we have h, a, t. Delta t. Where they have done here.
Yeah. So Doctor, just remember the question. He want to compare with fins or without fins?
Just remember the?
I just remember the question. You want to compare
With fins and without fins. Yeah. So first time we already found it with fins. Now we are finding it without fins, and then subtract the two to find out what is the increase. Is it clear? So here it is done. This is with fins, and this is without fins. So HA here is 2 pi R1H, and then theta B. So with fin, the heat transfer is 690 watt. Without fin, heat transfer is 236 watt. Well, that's good. That's a considerable increase, more than double. Okay. So addition of fin was useful.
Almost triple.
Hmm?
Almost triple.
Yeah, almost triple. So that's good. So anyways, that's this problem. So this topic is over. Is there anything in the problem that you did not understand? Is there anything?
Sometimes the area.
Yeah, it's complicated. I mean, it needs a lot of your concentration and involvement, but it is like that. However, for this question, did you understand how did we find areas and everything? That's good. RC? Which RC? From the question? Oh, that it was given in the form. It was given in the graph. What is RC? Let me show you. So R2C is equals to R2 plus T by 2. R2 is known, T is known. So you get R2C. Is it clear?
Yeah, we find R2 is like we add the length of the fence. So that R2 that's what from the center of the cylinder to the tip of the fence. They added the length of the actual fin itself.
Yeah. Just the actual fin. Okay. Okay, so now let's move towards the last topic for chapter number 3.
Next slide, and then it's done.
Okay, this is about thermoelectric power generator. Okay, let me drop this. Okay, in the thermoelectric power generation, now the thing is that there is a quality of materials that if I have a material and if I produce a certain level of temperature difference between the two ends of this material, automatically some potential is developed, some potential difference is developed between the two ends because of the temperature difference that can allow the electron to move from one end to the other end. So it's not just heat which will move from one end to the other end because of the temperature difference. Even electrons can also move. Okay, because of the difference in temperature. So because of the difference in temperature, there is a possibility that the potential difference is generated. Electrical potential difference is generated as well. This effect is known as Seebeck effect. Okay, Seebeck effect. Okay, so if I have a material and if I induce a huge temperature difference across it, so let's say this end I put it at 500 degrees centigrade, this I put it at 100 degrees centigrade. So huge temperature difference I place it, and because of this huge temperature difference, there is an electrical potential difference generated as well. Now the electrical potential difference generated is very little, is very less, but it is there. It will cause the electron to move from the high temperature to the low temperature. Okay, and when the electrons move from within the material, if we connect it to the circuit, it might take the load. Okay, but this potential, electrical potential developed is very, very small, and most of the times it is so small that it's not really useful. Most of the time it's so small that it's not really that useful. Secondly, this potential difference is a function of the material property. So you have a material, it will develop certain potential difference because of the temperature difference. Another material might develop a different level of potential difference because of the same temperature difference. So you change the material, and this potential difference development because of the temperature difference will vary. So it's a material property. So basically it is the semiconductors which are the best suited material for this job. Semiconductors are the material that if you generate a temperature difference across them, they have the highest possibility of generating maximum possible electrical potential difference for the electric current to pass. But even that potential difference is not that much. It's not a useful. Okay, so what we do is that first of all we make a p-n junction of semiconductor materials. So we produce the temperature difference not across just a single semiconductor material. We make a p-type semiconductor, we make an n-type semiconductor, we connect them, and we produce the temperature difference across them. Now there is a possibility of generating a little more amount of current. But still it is not useful because that little more is also very much less. So what we do is that then we connect many p-n junctions in series. 100, maybe 50, maybe 100 in series. We connect all of them in series so that the current from all of them together might become enough, sizable, so that it could be used. Is it clear? And this we make it in the form of one module. So one module has maybe 100 p-n junctions, okay, or 70 p-n junctions, all connected in series. But even the current from one module is sometimes not enough. So we connect then several modules in series. Okay? So actually, come to think of it, we are producing so much temperature difference, huge temperature difference, and we are generating very little amount of current. So it's not really that much useful. However, if there is some kind of heat which is in any case wasted, if there is a kind of heat, for example, you have a generator running on fuel, okay, the gas of the generator is very hot and probably it will be wasted. So what can you do with the energy which is coming out from the gas of the generator? It will go into atmosphere, it will be wasted. So if you take any amount of energy from it, it's good energy. Okay? So it is mostly used in places where the energy would ultimately be wasted. So you extract a small amount of it as electrical energy, that's good enough. Okay? So anyways, so we have thermoelectric power generation, as the name implies. Thermoelectric. It is the thermal energy which is causing the electricity to be produced. Is it clear? That's the thermoelectric power generation. Okay. So for that, what do we do is that we take the semiconductors, that's the n-type semiconductor and a p-type semiconductor. We connect them in series, make a p-n junction. Okay. On one end, now at the two ends, we need to produce the same temperature difference. So at one end, we will put a high temperature. At the other end, we will put a very low temperature. Okay. So what will happen is that because of the temperature difference, electric current might flow. So if we connect this circuit to a load, so there is a possibility of electricity to flow. Okay. And this flow of electric current, this production of electricity, is known as thermoelectric power generation. So you are generating electrical power by thermal energy. Is it clear? Now, you have to understand one thing. Suppose this is the body. This is my thermoelectric generator. Okay. So there are many, many PN junctions here. Okay. So I put very high temperature at the top, very low temperature at the bottom. Suppose at the top I put temperature 500 degree. At the bottom I put temperature 50 degree. Very low temperature, very high temperature, huge temperature difference. Okay. So it will produce a little amount of current. And suppose I connect it with a wire and with a bulb, so the bulb will light up. Okay. So, but what do you think? This is one material. And this is one material, and within this material, I put at one end very high temperature, at the other end at very low temperature. Won't there be energy transfer from high to low? That will be done by conduction automatically. So if I produce 500 degree here, 50 degree here, okay, and I leave it, after some time the temperature of the high temperature end will become less. So that will become from 500 to, let's say, 400, and this one will rise. This temperature will rise. It will become 50 to, let's say, 150. So now the temperature difference has reduced significantly. Previously it was 550, now it is 400 and 150. So temperature difference is reduced. The electricity production was because of the temperature difference. When the temperature difference reduces, so the electric current also reduces. And then the temperature difference will keep on reducing until they both are at the same temperature and no electricity generation at all. So it is the conduction through the material which is reducing the thermoelectric power generation. Is it clear? Now, in order to continue thermoelectric power generation, I need to keep this surface at 500 and I need to keep the bottom surface at 50. Okay? But I cannot stop conduction from happening. It's the same material. You produce temperature difference, conduction will happen. You cannot stop conduction. The only way is that you keep on supplying energy. So when the temperature of it drops from 500 to a little down, you supply more energy so that it keep at 500. And you keep on rejecting heat from the bottom. So when the temperature rises of the bottom from 50 to, let's say, 60, you reject heat and make it at 50 again. So you need a continuous heat supply at the top, you need a continuous heat rejection at the bottom to maintain the temperature difference. And then the flow of electric current flow or the power of generation would be continuous. Is it clear? So basically this is a conduction problem. This is a conduction problem. It is the conduction which is actually in this case reducing the thermoelectric power generation. Okay. So now it is like this. So suppose you have a thermoelectric generator here, thermoelectric generator, let me call it TEG, thermoelectric generator. Okay. So you have, this is a high temperature and you have low temperature side. So you have high temperature side, low temperature side. So for the high temperature side, if you want the electricity to continue to flow, so you have to keep on supplying heat at the high temperature side. And at the same time, you need to continue rejecting heat from the low temperature side. Okay? So now, first law of thermodynamics. If you are supplying heat Q1 at the high temperature side, then that's the total energy supplied. This energy will be converted into power plus energy rejected from down. Okay? So this high temperature side, so we have energy will be transmitted through conduction from high temperature to low temperature side. In the meantime, part of it will be extracted out as power, electrical power. Okay? And then this, so since part of it is taken out as electrical power, so not all Q1 will be gone to zero, to the low temperature side. So that will be, let's say this is Q2. And then you need to reject this Q2. Okay? So if I make the energy balance, so it's basically Q1 is equals to power produced plus Q2. That's the energy balance here. Is it clear? Now remember, this Q1 is very high, Q2 is very high, P is very, very small. So suppose Q1 is 1000, Q2 is 998, then P will be 2. So a lot of heat is required to be supplied, a lot of heat will be ejected, and very little electrical power is produced. But as I said, if this is the kind of heat which was even supposed to be rejected in any case, so even production of 2 is good enough. Is it clear?
Question. Q2 is high, like 998. Would it be the surface as hot as the other one?
Yeah, but comparatively cold. We are talking in comparison. So you'll see a numerical problem here, and in the numerical problem, one side surface is about 500 something, other side temperature is about 100 degree. 100 degrees is still hot, but anyways, it is slightly cool. Okay.
The power is enough to work or something.
Yeah, it's enough to produce a little amount of output. Maybe you need to light a bulb, maybe you need to charge a small battery or something like that.
It's free.
And it's free. The good thing is that it's free. Okay.
It is the same as the project?
Yes, exactly. Well, what he did was that, you remember we solved the problem for we solved the problem for the photovoltaic cells, and we saw that the efficiency of a photovoltaic cell depends upon the temperature, and as the solar energy keep on coming, the temperature rises. So when the temperature rises, efficiency drop. So he used that energy, part of that energy, to produce thermoelectric power generation. So that increased the efficiency of the photovoltaic panel. At the same time, some additional power generated because of the thermoelectric power generation. Okay.
Which energy to electric P1 constant? You said if I want to convert to Q1 to Q2, I need to give energy to Q1, electric 500, like sun. What energy?
Any waste energy.
Like what?
It could be sun, but normally not sun. Exhaust from the car or exhaust from a generator engine. Have you seen the diesel generators? Just put your hand in front of the gas where the gas is coming. Your hand will burn. It's hot. Okay. U1 plus P. Okay. Okay, so here you see we have a PN junction. Okay, so what we do is that above it we put a thin metallic conductor plate, and below we put a thin metallic conductor plate. Above the conductor plates we put insulation, so that we do not touch the generator and we get electrocuted ourselves. Okay, so insulation is important. So normally if you see these thermoelectric power generator modules, so you'll see a white thing, top and bottom. That white thing is the insulation actually, so that you do not get yourself electrocuted. Okay, and then we connect it with a circuit, and that circuit can take the load. Okay. So in essence, if you see here, so it looks like this. So you have multiple PN junctions all connected in series internally. Okay, then this is connected to an overall outside load. Okay, you are supplying Q1 high thermal energy at the top, and you are rejecting some energy from the bottom. Okay, and some power is produced. Okay, the length here is 2L. Okay. Okay, not because of the two sides. There's other reason for keeping it as 2L. It simplifies the problem solution. Okay. Now this is a very complicated problem, because the heat energy that you supply is going to determine the temperature of the hot side, which is going to determine the amount of conduction that is going to be conducted through the material, which will determine the amount of electrical energy produced. Everything is interrelated. Everything is interlinked. Everything depends on the other thing. Okay, so the problem solution becomes a bit more complicated here in this case. Anyways, we are not going to derive the formulas. We are going to use the end result. But the derivation is there in the book, and you are free to go and look into it if you want. These are the end results. So, okay, let's first talk about the thermal circuit. So, in the thermal circuit, if you see here, you have this is the hot side, top side of your thermoelectric generator, okay, and this is at temperature T1, suppose, and this is the bottom side of your thermoelectric generator, and this is at temperature T2, and between T2 and T1 there will be conductive resistance. Okay, so you have air or any gas, very hot, which is passing on the hot side. So you will have convective resistance here for that, okay, which will be here. So it will be from T1 infinity to T1. Then from T1 to T2, you have the conductive resistance, but in between, some of the power is produced by the Seebeck effect. Okay, so the remaining goes as Q2. Okay, and from T2 to T infinity 2, suppose you have a cold fluid running here. Okay, cold does not necessarily means cold in our terms, means comparatively low temperature. Okay, so you have a comparatively low temperature fluid, and it will have a convective resistance here. Okay, so that's the thermal circuit for thermoelectric power generation. So you have convection, then in between two things parallel, conduction and the thermoelectric power generation. Okay, and then after that you have the convection. So Q1, the end result, as I told you, we are not driving the formula here. The formula is derived. It's, I think, 2 to 3 page derivation in your book. Okay, it's a complicated problem. The end result is this. Q1 will be this thing. So this is what? 1 upon RT conduction module. So you have this module. So that's the resistance, conductive resistance of the module. That's the conductive resistance of the module, multiply by T1 minus T2, plus I is the electric current produced. I is the electric current produced into SPN effective. S is, as I told you, Seebeck effect. Seebeck effect means you have a material, and material has a property to produce some potential difference because of the temperature difference. So Seebeck effect is basically a constant, okay, and this is a material property. So you change the material, this Seebeck effect, Seebeck constant will change. So since we are using here p-n junction for semiconductor, so this will be provided to you as a constant, Seebeck constant for that. So that is SPN effective. Okay, it is given in the units volts per Kelvin. Okay, so how much voltage generated per degree temperature difference. Okay, multiply by T1 minus I square R effective. R effective here just remember this R is different from this R. This is the R resistance, conductive resistance of the module. Yeah, and this that is that R. Okay, and this is R effective is for the load, resistance of the load for power. Okay. Then you have the formula for Q. This was the formula for Q1. Okay. Then you have the formula for Q2. Formula for Q2 is the same as Q1, except that instead of T1 here, you have T2 here. Okay. And then you know that power generated is equals to Q1 minus Q2. As I told you, Q1 equals to P plus Q2, so P will be Q1 minus Q2. Right? So if you just subtract Q2 from Q1, you will get this result. Okay? So we have effective Seebeck coefficient we get from here. R conduction, as you said, it will be L upon Ka. Okay, so it will be L upon Ka, but A will be area of cross-section area of a single semiconductor multiplied by the number of semiconductors you have. Okay. So this will be the formulation here. Is it clear? The efficiency, how much is your thermoelectric power generation is efficient. Now in this case, if you see here, what is the input? Input is Q1. What is the output? Output is actually power. Q2 is there because if you do not produce Q2, then there will be no power. So basically efficiency is output over input. So efficiency will be what? P upon Q1, right? P is your output, Q1 is your input. So efficiency here is this, P upon Q1. Okay. However, you can also get the efficiency in terms of the Z values, okay, and it is given by this formula. If you know just the temperatures, it's the same way like you solved it in thermodynamics. You can get the efficiency by output over input, or you can get the efficiency of an ideal system where it only uses the temperatures. Okay, so here in this case it turns out to be this thing. It is using temperatures T1 and T2, but there is another terminology here, Z, where Z is this thing. Okay, so S square upon electrical resistivity of the semiconducting material. You studied electrical resistivity of the semiconducting material. I think you should have studied this in the course of electronics or introduction to what was measurement data acquisition. I think you've gone through this term. Yeah. Anyways, let's. So now we have a problem. We have a numerical problem related to it, and this will end this chapter, inshallah. Okay, we have an array of 48 thermoelectric modules. So how many modules do we have? 48 modules. Okay, installed on the exhaust of a sports car. So you have a sports car, and a sports car have an exhaust. Okay, and 48 thermoelectric modules are installed over there. Okay, each module has an effective Seebeck coefficient. So this is a Seebeck coefficient. It's given for the module. And an internal electrical resistance. So that's the resistance, electrical resistance, internal electrical resistance is provided. Okay. In addition, each module is of width and length. So each module is a square module. So width and length is same, 54 millimeter. Okay. And contains 100 pair of semiconducting pellets. So you have one module. In one module, you have 100 semiconducting PN junctions, and you have 48 of such modules, all connected in series. Okay, and they are put on the sports car. So it's shown here as well. You see, so that's the sports car exhaust, and they put modules like this, top, side, bottom, other side like this. So put all the modules like this, and connect all them in series. Okay. Each pellet has an overall length of 2L equals to 5 millimeter. Okay, and a cross-section area is also given. Okay, and is characterized by a thermal conductivity. That's the thermal conductivity of the semiconducting material. The hot side of each module is exposed to exhaust gases at. So you see the exhaust gases coming out of the sports car is at 550 degrees centigrade. Okay, and with the H1 is given. While the opposite side of each module is cooled by pressurized water. So the cold side is cooled by pressurized water at 105 degrees centigrade. So that's the cold side. Okay, so cold side is at 105 degree, and the hot side is at 550 degree. Okay, with and the cold side H2 is 500 watt per meter square Kelvin. If the modules are wired in series, Modules are wired in series. They will be wired in series, obviously. And the load resistance is, total load resistance is this. What is the electric power harvested from the exhaust gases? So we need to actually find P, but this is a very complicated problem. You will in the end make up 6 equations which you will solve simultaneously, because all equations have unknowns. Okay, so that's the schematic diagram here. You have, this is the exhaust pipe. The hot side will be inside the pipe, cold side will be outside. Okay, so hot side will have H1 given, cold side H2 given. Hot side temperature 550 degrees centigrade, cold side temperature 105 degrees centigrade. Okay, and each module has, these are square modules, have width and the length, width and the depth 54 millimeter. The thickness is 2L, is given 5 millimeter. This is 2L, 5 millimeter, their thickness. Okay, and there are 48 of such modules, and within each module there are 100 pairs of semiconductors. Okay, so this is all, and this whole thing is connected in series and attached to a load of 400 ohms. Is it clear? So this is a problem. Now, in order to find out Q1 or Q2, first we need to find what is the R conduction for the module. R conduction for the module is L upon Ka, right? So L we know because 2L was given. Okay, K for the semiconductor we know. Okay, and area for a single p-n junction we know, and then we know that there are 100 p-n junctions within one module. So n multiplied by this, so 100 multiplied by this, multiplied by K, L divided by this term, it will give you the R conduction for the module. Then we just substitute the values here. Now here Q1 is unknown, R conduction module is known, T1 is unknown, T2 is unknown. Remember, the temperatures that we know is not T1 or T2. These are the temperatures of the gases, the fluid. Okay, so there will be convective resistance from the fluid to the T1, and then similarly from T2 to the other fluid. Okay, so T1 and T2 are unknown. Obviously, I is unknown. S is given. T1 is unknown. I is again unknown. R is given. R effective is given. Is it clear? So many unknowns. Now we may make another equation, Q2. Again, I told you Q2 is the same as Q1, except that here it was T1, here now here it is T2. So all those unknowns which were there, if they are still unknown here in this equation. Okay. So how many unknowns do we have right now? We have Q1 unknown, Q2 unknown, we have T1 unknown, T2 unknown, we have I unknown, right? So 5 unknowns we have and 2 equations. Further move. Now we can generate, because you know the circuit is like this, that you have, this is T1, this is T2. So between T1 and T2 you have convective resistance. From T1 to T infinity 1, you have convective. And similarly from T2 to T infinity 2, you have also convection. Okay, so this is convection, this is convection. So we can use this equation here. Okay, so we can use an equation here like this. Similarly, we can use an equation here. Okay, so this is what? This is convective resistance. So Q is equals to HA delta T, right? So this Q is Q1. This is the Q1 here, and this Q is Q2. Okay. So Q1 is equals to H1. Now this Q1 is unknown. Okay. Area would be what? Area would be for a single module, its length into width, but this is a square, so it's W square. Okay. So area will be W square. This is known. H1 is known. Okay. T infinity 1 is known, but T1 is unknown. Okay? Again, you have two unknowns in this equation. You cannot solve the equation still. Okay? Similarly, you make an equation for Q2. So Q2 is in a similar way. So Q2 is unknown, H2 is known, W square known, T2 is unknown, T2 infinity known. Okay? So how many equations you have? Two equations in the last slide, two equations in this slide. So you have four equations, but still five unknowns. So you cannot solve it like this. Okay? So now what you do is that you can put another equation, and this equation was for the total one. You remember? We said that we have the equation here, Q1, Q2, and then we have an equation, this one, based on the first law of thermodynamics. Q1 equals to P plus Q2. So P equals to Q1 minus Q2.
That's a lot by 10.
Okay?
That's what they-
Yeah, because there are 48 number of modules. Okay? This is for a single module. So we put this equation here. This is the same equation, but multiply by m, because you have 48 modules here, because this is going to produce you the total power output. Okay? So putting all the values still here, in this case I is unknown, m is known, s is known, T1 is unknown, T2 is unknown, I is unknown, R effective is known. Okay? And then you have an equation, because in this case P total is also unknown. So now you have 6 unknown, 5 equations. Okay?
It's fine with this.
So now you have one equation from your electrical systems, the most simplest one. Okay? So the load is equals to I square R. Okay? So you say you substitute this. So now you have 6 unknowns and 6 equations. Solve them simultaneously, you will get what is the power output.
So what is P total?
So it's
We get this equation, this question in the
Fine.
previous
Fine.
student.
no, I thought I will give it to the summer ones.
Thank you. We don't care about mathematics, just what's the
Remember one thing, look, I'm not here to judge your mathematics. In case, if I give you a question which needs simultaneous solution, something that will require a lot of time of mathematics, then I will not ask you to solve it. I will just ask you to make the equations. Finish till here, no need for this step. Okay? And all marks will be till this point. However, I can modify the questions such that I provide you something so that you can solve it easily in one step. Okay? So if I give you the thing such that you can solve it in one go, then I can do that. Then I need the answer. But in case if I give you something that you need simultaneous solutions and you're not solving on computer, you're solving on paper, then I will not be judging your mathematics skills here. That will be judged in the mathematics courses. Okay, then I'll just ask you to develop the equations and leave. Okay? Is it clear? So with this, alhamdulillah, your chapter number 3 is over. You have some homework problems from chapter number 3.
Just sleep, I think.
Just little, small. Okay. So with this, chapter number 3 is over. Inshallah, we are about to start chapter number 4 now. So we are already done with chapter number 3, which was about conduction, one-dimensional steady state. Okay, and as you have gone through this chapter, you might have realized that although it is one-dimensional, an analytical solution was still not that easy. With internal heat generation, the questions become way more complicated. Then you have to specify the boundary conditions and things like that. It becomes, I think it's recording. So with the boundary conditions, things becomes a bit more complicated. Now that was one-dimensional heat transfer, and it was still doable, although a bit complicated, but still doable. Now we come over to the two-dimensional or three-dimension heat transfer. Well, that becomes really difficult. You have partial differential equation of second order. Okay, you remember the heat conduction equation. Heat conduction equation was what? Was Q dot plus dou by dou x, K dou T by dou x, plus dou by dou y, K dou T by dou y, plus dou by dou z, K dou T by dou z, is equals to rho Cp dou T by dou dt, right? So when you have two-dimensional case, that means only z term is not there. Even let's say it is a steady state, so this is not there. So you end up with this thing, Q dot plus, if it is isotropic, most of the time we have, so this is K dou y square T by dou x square plus K dou y square T by dou y square equals to 0. Okay, or I can say that, put this K here down. So this. Now it's a second order partial differential equation. Second order partial differential equation. That was a full differential. Okay, that was a full differential in the one dimension. It was second order, you need two boundary conditions. Now here, second order partial differential equation, solving it, finding t. Now you need to find not just t as a function. Previously you were finding t as a function of x. Now you need t as a function of x and y. Or it makes the life a lot more difficult. This is not really easy. So anyways, the whole solutions that we used to do in the last chapter, those solutions we used to call them analytical solutions. The ones which you can solve by using integration, differentiation methodologies, they are known as analytical solutions. Okay, but finding analytical solution for partial differential equations, second order, second degree, it's really not that easy. Okay, so what we do is that we move towards the other methodologies. We move toward other methodologies. Analytical solution, not easy, and in many cases not possible either. Okay, so when the analytical solution are the exact solutions. Exact solutions are really very accurate. Okay, but now since we have now limitation that in the second in the two-dimensional and three-dimensional cases, analytical solutions are not easy and in many cases not possible. So now we have to move towards comparatively less exact solutions. So these are the exact solution, but exact solution if not possible, then we have to move towards approximate solution. Okay, so one way is that going towards the approximate solution, so we have an approximation methodology, and then we move towards numerical solution. Okay, so numerical solutions are the most easy answer to these problems. Okay, but they have their level of accuracy. Okay, and secondly, then they have their computational method. Okay, and so what you do is that in case of numerical solution, okay, we'll go to it. We will go with it. So let's talk about the alternative approaches. So what alternative approaches do we have? We have the exact solutions, but they are not really that possible. Then we have the approximate solution. We get it using the shape factors. So we make some approximations and still like solve the problem analytically, but with some approximation. Okay, so first we simplify the problem a little, solve them, then solve them analytically. So that is by using the shape factors. And the third way is that using the numerical method. Numerical method means either using finite difference or finite element method approach. Okay, so as we developed here, that actually what we want is that we need to solve this equation, okay, if there is no internal heat generation. Dou y squared theta by dou x squared plus dou y squared theta by dou y squared equals to 0. And we need then 4 boundary conditions at least, okay. And what is the methodology analytically if we want to solve? Then by using the method of separation of variables you can solve. Do you remember the method of separation of variables? You might have gone through it.
The x together and y together.
Yes.
Integrate.
But it's a very long procedure and it's a very long solution. And in most of the cases, it's not even possible to solve it like that way. Okay, in some cases, yes. And the solution comes in the form like this. Okay, so they are really complicated ones. Anyways, this is just an example given. We don't need to go through them. Okay. So the next is the approximate solution. In the approximate solution, what do we find is that we find is the shape factor. Okay. So basically, what do we have? We have Q is equals to, we find it like this. We find it Q is equals to Sk delta T. Okay. Now Sk, we consider it as similar to resistance. So Sk is equals to 1 upon resistance. Okay. Sk is the shape factor. And the formula for this Sk, or that means the formula for the resistance, is actually predetermined. Okay. By putting some approximations, the formulation is already developed, okay, for many cases. So by using this formulation developed, we can actually solve the problem. Okay. Now these developed formulation are presented in the form of a table, and that table is a part of your book of your tables. Okay. This is table 4.1. So suppose you have a ball which is dipped in semi-infinite medium. Okay, semi-infinite medium means it is an infinite medium, but the medium itself has a boundary. So for example, it is dipped in water. So water is considered as an infinite medium for the ball, but water itself has a boundary layer defining. Okay, so it's kind of a semi-infinite medium. So heat transfer could be approximated from the ball. Let's say the ball is hot and the water is at different temperature. So heat will be transferred from the ball to the outside water. And this heat transfer could be approximated as a two-dimensional heat transfer. Okay. And in this case, if now for these cases, you have some limitations. Okay. And for example, in this case, the limitation is that from the surface of the water level, the ball should be, if the distance of the ball, center of the ball from the surface of the water level is z, then z should be much greater than d by 2. That means the ball should be much down in water, not close to the surface. Okay. So the ball should be fully dipped in water. If the ball is fully dipped in water, then we can use the shape factor, this approximation here. Okay, to find out the heat transfer from the ball to the water. But if this condition is not justified, is not satisfied, then we cannot use this formulation. Is it clear? But if this condition is satisfied,
Cannot find this statement or something.
this is a restriction. So in order to apply this shape factor approximate solutions, you need to satisfy these restrictions. If this restriction is not satisfied, then you cannot apply it. Okay. So this is just one example. Okay. So because of these shape factor formulas given, things becomes a lot easy. For example, here you need to find Q. If you know the delta T, the only problem is in the resistance. How to find the resistance? Resistance for two-dimensional is all the problem that you have. Okay, so here that resistance formula is directly given. 2 pi d upon 1 minus d over 4z. Z is this depth. D is the diameter. So substitute this, you will get the resistance, substitute the resistance here, you will get Q. Is it clear? So this is an approximation, this is an approximate methodology. Why approximate methodology? This result you get is by analytical solution, but they made some approximations, they make some, they simplify the problem a little in order to get this answer. So there will be some error, but the error is considerably acceptable. Okay? So this is one case. Then you can have another case. For example, if you have a horizontal isothermal cylinder of length L buried in a semi-infinite medium. So for example, you have a rod like this, and if this rod is dipped in water, okay? If this is the case, that was for the case of a ball. If this is the case of the rod, then this second case can be applied. Now for the second case, if L must be greater than D, length must be greater than diameter, then I can use this formula. And if L is greater than D but Z is greater than 3D by 2, then I use this formula. Okay? So anyway, it's just a matter of, now how would you determine which case you have to use? You have to see yourself. Is it like a rod dipped in water? Is it like a ball dipped in water? Is it like this case that you have a vertical cylinder which is at the surface of the water, dipped, but at the surface here? Okay? So you have to visualize yourself which condition satisfies your case. And then once you visualize that, then it's just a matter of pick and plug. But while you're picking and plugging, you have to make sure that all the constraints are satisfied. If the constraint is not satisfied, then your answer would be that we cannot apply it because the restriction is not satisfied. Okay? It is restricted to use this formula only under these conditions, and these conditions are not satisfied. Is it clear? So this is, I put here only one page, but this is not one page. This is case 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, something like that. So 14 cases you have, or more than 14. But all of these are there in the table.
About the symbol, L is greater than D or greater than or equal?
This is greater. When it is said this, that means much greater than D. When you say like this is greater than equal to. Okay? Okay, so let's come over to the formulation. Let's come over to directly a solution. Okay. We have a metallic electrical wire. Let's have a metallic electrical wire of diameter 5 millimeters to be coated with insulation of thermal conductivity. It is expected that for the typical installation, the coated wire will be exposed to conditions for which the total coefficient associated with convection and conduction is H equals to this. To minimize the temperature rise of the wire due to the ohmic heating, the insulation thickness is specified so that the critical insulation radius is achieved. During the wire coating process, however, the insulation thickness sometimes varies around the periphery of the wire, resulting in eccentricity of the wire relating to the coating. Relative to the coating. Determine the change in the thermal resistance of the insulation due to an eccentricity that is 50% of the critical insulation thickness. Now, the thing is that you have seen electrical wires. That's an electrical wire there. Okay, if you see these electrical wires, the electricity is passing through the electrical wire, which is actually inside. Outside is a coating, and the coating is of insulation. So you place insulation so that you do not get yourself electrocuted, and you don't want the heat, because the wire gets heated, you don't want that heat to be that wire to get hot. Okay, so you put insulation there. So this insulation is done, and normally it is assumed that the insulation is concentric. Concentric means if the wire is like this, then the insulation is like this, such that the center of the insulation is the same as the center of the wire. They are two exactly have the same centers, the insulation and the wire. But there is a possibility that sometime it happens that while you are putting the insulation on the wire gets a little eccentric, opposite of concentric. Concentric means same centers, common centers. Eccentric means there is some displaced, centers are displaced. So there is a possibility that the insulation is like this and the wire is like this. Okay. So in this case, although here the thickness was all same all around, but in this case the thickness here drops and here thickness rises too much, okay, for the insulation. Now when you have the rise in thickness, that's not a big issue, but when you have a drop in thickness, now there is a problem, because the problem is that maybe it will become too hot, maybe it will burn, maybe it's not going to provide that much resistance. Okay. So this insulation thickness is providing the resistance. Now the resistance here has increased, but the resistance here has decreased. Okay. So now this is what it says. The problem says that we need to find out what is the change in the thermal resistance. What is the change in the thermal resistance if the wire is eccentric 50%? Okay. So if the thickness was here T, so now this distance is now T by 2, because it's 50% displaced up.
Multiplied by 2 in the other side.
Not multiplied by 2. So it will be T plus T by 2 on the other side. Is okay? So that's the problem. Okay. Now now they did not tell what is the critical thickness. I mean, what is the thickness of this insulation? They did not tell that. What they say is that the thickness, insulation thickness, the insulation thickness is specified so that the critical insulation radius is achieved. Now, what is the critical insulation radius? Critical insulation radius is something that we did not did in chapter number 3, but there was an example. I said that you do it yourself. And that example proves the formula for the critical radius of thickness. I've explained it to you that why that criticality is important. Why is that so critical? Because if you make thickness higher than that, then it will not give you more benefit. Instead of dropping heat transfer, it will raise the heat transfer. And I explained the reason for that. But I did not go through the problem myself. I said that go through it yourself. However, the formula for it was given in the formula sheet. Okay. And it was, I think, K upon H, something.
Yeah.
K upon H. Critical thickness is K upon H. Critical radius. So now, objective is that we need to find what is the change in the resistance. We need to find what is the change in the resistance. Okay, that's the objective. Now, critical radius is given by this formula, K upon H. Okay, critical radius is given by the formula K upon H. Now, K is provided to you, H is also provided in the problem. Okay, so now you get what is the critical radius. Okay, so that's the critical radius here. This is our critical. Okay, it is provided to you that what is the diameter of this wire. Diameter is known, that means radius is also known. Okay. So if the radius of the wire is known and the critical radius is known, we can find out what is the thickness of this insulation. Okay. So it's this radius minus this radius. Okay. So it's this thing. So that will be the thickness of insulation. Okay. Now, if we know what is the thickness of insulation, we can actually find out what is the resistance from it. If you see here, the resistance from this insulation can be found out using ln R2 upon R1 divided by 2 pi Lk, right? That's the resistance. So R2 will be the critical radius, R1 will be the radius of the wire, 2 pi Lk. Okay. So from this we can find out what is the resistance. Here they found out resistance per unit length. That's why L is not there. It's the resistance per unit length. Okay. So they get out what is the resistance. So now we need to find the change in resistance. So we know what should have been the original resistance. But in our case, the thickness now here is changed because of the eccentricity. Okay. So now I need to know what is the new resistance. And the resistance is this Sk. Resistance is this Sk. So from the table, it's I think case number 7, we can directly find out what will be the resistance if you have a certain eccentricity. So the center here is this, center here is this, and if there is a change in center, let's call this Z. So if you have an eccentricity, then what will be the resistance? So we find out the resistance using the formula there. We already know the resistance for the original case. The change in resistance is what we needed to find. How much is the change in thermal resistance? So our resistance for this case is given by this formula. Can you see it in the table?
Yeah.
Okay. Now, because it is 1 upon Sk. We want to find the resistance which is 1 upon Sk. Okay. So now we just need to substitute the values. So now we just need to substitute all the values and we will get the new resistance. So previously we had a resistance, now we had a resistance. We can see how much is the change. It's not working. What do you mean it's done? Okay, so can we make it for 10 more minutes as possible? Okay, okay.
So everything nothing good.
Huh?
So if
No, no.
No, I mean the sound.
The sound.
Yeah. Now it's working now.
Oh, the sound was
Yes.
not working?
What? It's okay.
Hello, hello, hello. Can you speak? Yeah.
Okay.
The sound was not working before?
No. I think it wasn't because the wave.
Okay. Anyway.
Go.
Okay. So it can work. It's working. Okay. Just a little more. Okay. Anyways, do you understand the methodology that I have explained here, that we have done this? Okay. Now we have another problem. Okay. In this problem, it's an internal corner of solid with convection. So it's kind of a same problem, but now on one of the corner here, this corner, we have convection. So the solid material is not there. You see, solid material is not there. We have convection here in this corner. Okay. So again, it's the same energy balance. It's the same energy balance procedure. Now in this case, I think the heat transfer, the heat generation is also not there. Okay. Heat generation is also not there. If the heat generation is not there, then this will be zero. Okay? In this case. Now in the second case that we are solving here.
They said it's a
There is a connection. They did not say it, but if there is heat generation, then it is specifically mentioned that there is heat generation within the solid body. Okay? So here they don't say anything about heat generation, assuming there is no heat generation. And whenever there will be heat generation, it will be specifically said that there is heat generation. So in this case now it will be what? E in equals to 0, that's it. Okay? So if you look here, now this is our control volume. Over this control volume, we will have heat conduction from this end. It will be the same. The heat conduction here will be the same as you did before. Right? You will have heat conduction from this end. Again, it will be same as you did before. No change. But now you have heat conduction from here. But in this case, if you see one thing, that area is half. So just one thing here, that instead of putting delta y, it's delta y by 2. Instead of putting delta x, it's delta x by 2. That's it. No further change. So here the conduction from here, area is half. Here the conduction from here, area is half. Is it clear? So 4 conductions in the same way, except that in 2 of the conductions, area is half. Okay? Other than conduction, now you also have convection here. Okay? So convection will be what? Convection is H A delta T. Right? Convection is H A delta T. So you have one convection in this direction, one convection in this direction. Okay? So it's both direction H A delta T. But in one direction, in case, A will be delta x by 2, other A will be delta y by 2. Is it clear? So that's the thing. So if you see here, convection, H A delta x by 2, T infinity minus Tm minus n. H delta y by 2, T infinity minus Tm minus n. Is it clear? So now you have 6 Qs, 4 Qs for conduction. This considered as 2 Qs for convection. Add all of them together in one equation. Summation delta Q, summation Q equals to 0. Add all of them together, put delta x equals to delta y. You're going to end up in this with this equation. Okay? I developed this equation myself here. Okay? So that was 1 Q conduction, other conduction, third conduction, fourth conduction, then convection, then convection. All of these conduction plus convection together get this thing, then assuming delta y equals to delta x and dividing by k, we come up with this equation. suppose this problem comes in the exam, you have to develop this equation. You have to do it like this. It's like a proof. Okay? So this is a generalized equation for this case. Okay? You have another table here. This table is not provided to you in the book of tables, because for different cases, these are the end results. For different cases, these are the end results. Some of them are present in the homework problems as well that you have to develop. So those which are present in the homework problems are important in the sense that I can ask you to develop them. Okay? The procedure would be the same. Consider the control volume, see all the conduction convection. If there is heat generation there or not, add them all together, okay, divide by delta x, delta y. Okay, consider that. Now this is another problem, same problem, but only one thing. Now you see here, this is delta x by 2. So your conduction from here will be half. Conduction from here will be half. Conduction from here will be full. And from this side, it's written insulated. So no conduction, Q3 0. Okay, that's it. So if you see here, solution here, Q1 plus Q2 plus Q3 plus Q4, and then there is heat generation. Okay, so Q1 full, Q2 half, Q3 0, Q4 half. Just add everything together, end up with this equation. That's the answer. That's it. Same procedure, no change in it. Okay. Then next one is a homework problem. Okay. After developing these equations, then we can solve it using the matrix methodology. But we are not going to go into that. It's there in your book. If you want to go through it, you are most welcome. Okay. So, anyways, after that, this is basically a homework problem. It's there, the solution is also provided here, but it is a part of the homework problem actually. So go through it, and if you have any problem, you can discuss. Okay, and that's it. With this, our chapter number 4 is over. Okay.